Welcome to the deep dive. Today we're digging into a really fundamental question for AI. How well do image classifiers actually work when they see stuff that's just a little different from their training?
Exactly. We've got this analysis here looking at AI model behavior, and it's quite revealing.
Yeah, so our mission today for you listening is to get a quick handle on this challenge AI generalization. Basically, its ability to handle new things, but without drowning in technical jargon.
Right. And we're focusing on a case study that really highlights just how sensitive these models can be to small changes.
Okay, let's dive in. First up, local 8 global generalization. What's the big idea there?
Well, think of it like this. An AI might be great, really spot on with its specific training pictures, that's the local,
Okay.
but throw something slightly different at it, something from the messy real world at the global, and it might stumble.
And this study uses clocks to show that.
Yeah.
Tell us about Model A's training.
Yeah, clocks. So Model A, it was trained mainly on pictures of analog clocks, the ones with hands.
That traditional clock.
Right. And crucially, very few examples of digital clocks in that training set.
Got it. So naturally, they tested it with something a bit outside that comfort zone.
Exactly. They showed it a digital clock.
Right.
But not just any digital clock. This one also displayed the date and the temperature quite prominently.
Still a clock.
Yeah.
Fundamentally, but with extra bits. So how did the AI models, and there were several, right? How did they cope?
Yeah, 9 different models, including some pretty advanced ones like vision transformers and efficient net. And the results were, well, frankly, a bit chaotic.
Chaotic. How?
Some models did correctly say clock. That's what you'd hope for. But others, they misclassified it completely as a window, even a door in some cases.
Wow, a window or a door. That's
Yeah.
surprising. It really shows how those extra elements, the date and temp, could throw them off.
Definitely. There was no clear consensus at all.
And the text suggests overfitting might be a reason.
Overfitting is, yeah, a likely culprit here. If the model trains too tightly on just those analog clock images, it gets really good at those specific images.
But not the general idea of a clock.
Precisely. It's like it memorized the training set rather than learning the, essential features of what makes any clock a clock.
Okay, so that was Model A. How did they try to fix this with Model B?
With Model B, they really broadened the training data, expanded it quite a bit.
How so?
They trained it on 47 different object categories. So it included the original 29 categories Model A saw, plus 18 totally new ones, just giving it more visual context, essentially.
Right, a more diverse visual diet, as you said.
Mm-hmm.
And did they test Model B on that same tricky digital clock?
Yep, the exact same image. Digital clock, date, temperature, the works.
And the results? Better, I hope.
Better, yes. Definitely more consistent. This time, 7 out of the 9 models correctly identified it as a clock.
Okay, so improvement, wider training help build consensus.
Uh.
I sense there's a but coming. The text mentioned low confidence.
Yes. That's the really interesting part. Even though most models got it right, their confidence scores were noticeably low.
So they said clock, but kind of mumbled it. What does that low confidence tell us?
It suggests what the analysis calls a data discrepancy. Basically, even though the image was a clock, its specific appearance, those prominent date and temperature digits, was still different enough from the bulk of Model B's training data.
That it made the models hesitant, less sure of themselves.
Exactly. It caused uncertainty. So the classification was right, but the low confidence is like a little warning flag.
Okay, so summing up this first case study then, what are the key signals we should look for when thinking about generalization errors?
2 main things jump out from this example. First, for Model A, that complete lack of agreement, the wildly different labels, that's a big red flag.
Right. Window, door, clock, all over the map.
And second, for Model B, even when most models agreed, those low confidence scores are crucial. They signal that the model is working outside its core comfort zone, even if it gets the right answer. It points to that data discrepancy.
So, for you listening, the takeaway seems pretty clear. Even tiny differences, things that seem insignificant to us, between training data and real-world examples can seriously mess with an AI's performance. It's not just about getting a high score on a test set.
Absolutely. Accuracy numbers alone don't tell the whole story. And that leads to a final thought for you to chew on.
Yeah.
Think about where else AI is being rolled out. Medical scans, maybe? Self-driving cars? Financial fraud detection?
Areas where subtle variations are everywhere.
Exactly. So, how might these same limitations, the sensitivity to slight, unexpected differences, cause problems in those systems? What kind of real world variations, things not perfectly captured in the training data, could cause an AI to falter, even if it seems incredibly accurate in the lab? Understanding those boundaries, knowing where the AI's knowledge gets shaky, is just critical.